So as long as you can use the combined gas law, you know all of the other individual gas laws. So we're just going to do this warm up today. And then again, let's remember what our combined gas law is. It's P1 V1 over T1 equals P2 V2 over T2. This is the combined gas law. Sometimes there's moles in here. This is the true way, but usually the moles are considered constant because you're looking at one gas that's changing. We'll talk about when the gases change to other gases later. But for now, this is the most common way you see the combined gas law. So then what you do is you focus on what is given in the problem. So we have sulfur dioxide gas. It has a volume, so that's V, and a temperature, so that's T. And they say at what temperature, so that's another T, will the gas have another volume, so that's another V. So then you go, okay, they did not mention pressure anywhere in here at any moment. So it's assumed to be constant. So I'm just going to ignore it. Like, I'm going to get rid of it. I'm going to pretend it's not in there. And if you just get rid of it, this is how volume and temperature are related. In fact, this is Charles' law. It's Charles' law without the pressure in it. So now we're just going to plug and chug. Now, the hardest problem that kids have with these ones where you're solving for something in the bottom, this is who we're trying to find. You cannot solve for it while it's in the denominator. You have to get it out of the denominator. So you either do that by cross multiplying, if you know what that means. That means you just take this guy and put it up here. You go across. Or the same thing is just multiplying both sides by that. Okay? And that will get rid of it over here, right? Now that it's not in the denominator anymore, you can solve for it. So how do I do that? Well, I multiply both sides by the reciprocal, so I can get this guy over here. It's also the same thing as cross multiplying. So V1 comes down here, and T1 comes up here. It's the same thing as multiplying by T1 over V1, right? Because that will cancel over here. T1 over V1. Same thing. The only other trick in this problem is to make sure your temperature is in Kelvin. You cannot leave it in Celsius. So what is V2? V2 was 1.25 liters. That was the second volume given. What is T1? 23 Celsius. No. So you add 273 to it to get Kelvin. So 296 Kelvin divided by V1 is 1.16 liters. So liters cancel, and we're left with Kelvin, which is great because that is a unit for temperature. So 1.25 times 296 divided by 1.16. Sig figs. This is multiplication and division, so you use the one with the least. This is 3, this is 3. I do realize that this is 2, but you didn't plug 23 in here, you plugged 296 into here. So 3, 3, 3, your answer should be 3. So 319, and if I asked you to convert it back to Celsius, you would subtract 273. So to get to Kelvin, you add 273. To get to Celsius, you subtract 273, and that would be 46 Celsius if you were to go back to Celsius. So the temperature is 296 because we had to convert Celsius to Kelvin, and the way you do that is by adding 273. So Kelvin temperature is whatever you have in degrees Celsius plus 273. That's like the conversion factor. So 23 plus 273 is 296. That's how you take anything that's in Celsius and convert it to Kelvin. And we can only use Kelvin in here, in these problems. Okay, the next topic is called Dalton's Law of Partial Pressure. And basically, Dalton's Law just says that if there are a bunch of different gases in a container, they all contribute to the total pressure. So like the room that you're sitting in, our room right now in this classroom, there's a bunch of different gases in here. There's nitrogen gas in here. There's oxygen gas in here. There's a little bit of argon. There's probably a tiny, tiny bit of CO2. But there are a ton of gases in here, and they all make up the total pressure. So if you add the pressure of all of the gases, they will add up to the total pressure inside this room. That's all this is saying. Each gas has its own pressure to make up the whole pressure. That's all. So air is made up of 4 main gases. It's really 3. Carbon dioxide isn't really that high, but whatever. Okay. And we say air pressure, the pressure of the air at sea level is about 760 millimeters of mercury. This is the same as 1 atmosphere. Okay. So like because we live in Huntington Beach, we're basically at sea level. So the pressure of our room is probably pretty darn close to this. This probably would not be true somewhere high up in the mountains, but for us, this is pretty true. So it says calculate the partial pressure of oxygen if we know the pressure of nitrogen, the pressure of argon, and the pressure of carbon dioxide. Well, what does this mean? This means the total pressure, P total, in a room is equal to the pressure of nitrogen gas plus the pressure of oxygen gas plus the pressure of argon plus they also included CO2. So if you know total pressure, they told you it was 760, right? And you know this guy, and you know this guy, and you know this guy because they gave you all those numbers. Can you find oxygen? You just subtract them all, right? So the pressure of nitrogen, what was it? Nitrogen was 594 in the problem. So 594 millimeters of mercury. Plus, we don't know oxygen, the partial pressure of oxygen. Plus, they told us argon. They said argon's pressure was 7.10. Plus, carbon dioxide's pressure was 0.27. So you have 2 options. You either subtract 594 from 760 and then subtract 710 and then subtract 0.27, or you can combine all of these at once and then subtract them as a whole. It doesn't matter. It's up to you. So I'm going to combine them all. So 594 plus 7.1 plus 0.27 is a total of 601.37 millimeters of mercury. I combined these 3 guys. And then I don't know oxygen. So now I just subtract. Oops. All right. So this is just subtraction. So the partial pressure of oxygen gas is 159 millimeters of mercury, which would be the same thing. I know it's been a while, but this would be the same thing as 159 torr. Remember, these 2 units mean the same thing. This is the actual measurement because they measured it with like a legit ruler, and this is the scientist Torricelli who did it. Okay, so it's very apparent that the most pressure comes from nitrogen. The second most pressure comes from oxygen. The third most comes from argon, and the least comes from carbon dioxide. So this is called Dalton's Law of Partial Pressure. Okay. So this is everything that I just did on that whiteboard.
How come it just said 158? Like, I looked and the answers in like the back, like at the
It's 158.63, but when you follow sig figs, you go to the ones place because you're subtracting. So this goes to the ones place, this goes to the hundredths place, so you can only go to the ones place. So it's 158.63. And if we can only go to the ones place, that's right here. So 6 is high enough to round that up to a 9. Okay. So let's try another one. What is the partial pressure? So just partial means part. It's part of the total pressure in a mixture of nitrogen gas and oxygen gas, okay? So in the container, the total pressure is coming from part of it coming from nitrogen gas and part of it coming from oxygen gas. The nitrogen and the oxygen combine to give you the total pressure in the container. Now, it looks like they're asking what is the partial pressure of oxygen? So that's this guy right here. And they give you total pressure and nitrogen. This is much simpler than the other problem. So partial pressure, if I'm going to rearrange, right, I would take and subtract nitrogen from both sides. So total pressure minus the pressure of nitrogen gives me the partial pressure of just oxygen. This is algebra. You move this to the other side by subtracting it. The reason we subtract and don't divide is because these aren't being multiplied, they're being added together. So what is total pressure? 0.48 minus, so total pressure minus nitrogen is 0.24. Well, this is easy math. It's 0.24, right, in this container? So the pressure of the oxygen is the same as the pressure of the nitrogen. They're both 0.24 atmospheres. So basically 50% of the pressure is coming from nitrogen and 50% of the pressure is coming from oxygen. Okay. Let's try again. Find the total pressure. So that's pressure total of a mixture that has 3 different gases, and they don't tell you who they are, but they give you their pressures. Well, total pressure is going to equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas. So we're just literally adding all these numbers together. Total pressure equals 6.6. Remember, kPa stands for kilopascals, plus 3.2 plus 1.2. Now, sig figs, because we're adding, you follow the decimal place. Tenths, tenths, tenths. So your answer should go to the tenths. So 6.6 plus 3.2 plus 1.2. Ooh, it is 11, but you have to have a tenth spot holder, so you put 0.0. And then the units are kPa, kilopascal. That is just an alternate unit for pressure. It's kind of like mass. Like we can measure mass in grams, kilograms, pounds, ounces. Those are different ways to measure mass, just like there's different units for pressure. Okay. Okay. So if you remember the kinetic molecular theory was for ideal gases. And this theory made some assumptions that we make about gases to make our life easier. Because that theory allows us to use this equation known as the ideal gas law. It follows the kinetic molecular theory. This equation, believe it or not, is not that complicated. Once I show you what the real equation would look like if we didn't have the kinetic molecular theory, this won't seem so bad. Now this takes into the gas law concepts the fact that, pressure and temperature are directly proportional, volume and temperature are directly proportional, pressure and volume are inversely proportional, and combines it into what's known as the ideal gas law. So where P stands for pressure, V stands for volume, N stands for moles, R is called the gas law constant, and you don't need to memorize it. It will always be given. You just need to know how to use it, okay? And then T stands for temperature in Kelvin. Okay? This is what we would have to use if we did not follow the kinetic molecular theory. This is a true equation to find pressure or volume or temperature of real gases, okay? And gases are real because they're really around us, but if we follow the kinetic molecular theory, we can use a much more simplified version to find out a pressure or to find out a volume or to find out a temperature. This makes our life easier, unless you would rather do math with this equation, which I don't think anybody does. So that's why the kinetic molecular theory helps us to solve for pressures or volumes or temperatures, because by making these assumptions, we get to use this like beautiful, nice, ideal gas law instead of this horrific, kind of complicated gas equation called the van der Waals equation. Okay, we're not ever going to use this equation. We're always going to use PV equals nRT, and I'll often refer to it as pervnert, not pervert, pervnert. Okay. The ideal gas law has R constants. Again, you don't need to know them in terms of memorizing them. You just need to know how to use them. And the constants units are kind of complicated. So I want you to take a moment and look at the different R values. So again, you don't need to memorize these. These will be given to you on any test if you need them. Okay? If you look at their units, they only differ by one kind of unit. So look, they all have liters in them, right? What else do they all have that's the same? Moles, right? Moles, moles, moles. What else do they all have that's the same? Kelvin, Kelvin, Kelvin. So what is the difference? It's the unit for who? Kilopascals, atmospheres, and millimeters of mercury measure what? What do they measure? What property? Oops.
Pressure.
Pressure, okay? So that's the only thing they change by, are units of pressure, okay? So this one is for pressure in kilopascals, this one is for pressure in atmospheres, and this one is for pressure in millimeters of mercury, or torr. Don't forget about torr. So we'll practice. Now, this says what pressure, and then they say in atmospheres. This is important because they tell you what unit they want the pressure in. And then they give you 18.6 moles. What does mole represent? N. The letter that represents moles is N. And then it says it's methane gas and it's compressed in a 12-liter tank. So that's volume. And I gave you temperature, T. Now, what pressure is P? How come, the question becomes, why is this not helpful? Because until now, we'd been using like combined gas law, or at least one version of it, right? Why is combined gas law not going to help us in this problem? If any of the gas laws you usually have two of the same thing. Like maybe you have two volumes or two temperatures or two pressures, okay? I don't see two of any variable right here. I only see one of the moles, one of the volume, and one of the temperature. To use this, you need to have two of at least one of them. You need to have like two volumes and a temperature, or two pressures and one volume, or two pressures and one temperature. I don't have two of anybody here, so combined gas law is out. It will not help us with this. So this is where the ideal gas law, referred to as PERV-NERT, comes in. So let's look at our new law. Let's rewrite it. PV equals nRT. I'm trying to find pressure, right? So how do I get pressure? I get rid of volume on that side, right? So I divide both sides by volume. So pressure equals moles, which I have. R is a constant, which you will always have because you can look it up. T is temperature, and V is volume. This is plug and chug. I have everything I need right here for this problem. So let's start plugging in. So the moles are 18.6, that's N. Now, the R constant, you have to go back and look it up. So here are three options that we have. It will be one of these three. The question becomes is who do I pick? Which one should I pick? Should I pick this one or this one or this one? These are three options. They asked you for the pressure in what unit?
They asked for atmospheres.
Atmospheres. This is the one that has atmospheres in it. So this is the R constant you should use. That's how you pick. So that's the one I'm going to use. I'm going to use 0.0821. So the R constant, 0.0821 liter times atmosphere over mole times Kelvin. So there's R. I have N, R. T needs to be temperature in Kelvin. The temperature given was 45 degrees Celsius. So you can't use 45. To get Kelvin, to get Kelvin, you take 273 and you add 45 to it. So 273 plus 45 is, 318 Kelvin. And nRT divided by volume. You guys have the volume? Sorry. The volume was 12.00 liters. Okay. I want to show you, before you do any of the math, I want to show you how the units work out. Look at, there's a mole right here, and then there's a mole down here. They cancel. Kelvin right here, Kelvin down here. They cancel. Liter, liter cancel, and we're at atmospheres, which is pressure. So you do 18.6 times 0.0821 times 318 divided by 12. Give you a second. And it looks like the answer is 40.5 atmospheres. This is like a lot of pressure. The pressure of this room right now is 1. 40.5 atmospheres is a ton of pressure. Okay. Any questions? All right. Now they're going to make it a little bit harder. They say, what is the volume? So we're trying to find V occupied by 35.4 grams of nitrogen gas, and I give you temperature, and 735 torr is a pressure. Again, combined gas law does not look like it will be effective. Like, I don't see two pressures or two volumes or two temperatures or two of anything. So the only other equation we really have is PV equals nRT, ideal gas law, Pervner. And I want to find volume. So how do I get volume by itself? I divide both sides by pressure. So nRT over P is volume. Now, I have temperature, right? It's right here. I have pressure. It's right here. You will always have R because it's a constant and you can look it up. And I don't have moles. That's something that there's a little issue with. Do I have something that can get me to moles, though? Can you turn grams into moles to be able to use? And that answer is yes. This is old stuff. If you know the grams of nitrogen gas, you can know the moles of nitrogen gas. So how do we do that? We say, what's it, 35 grams? 35.4 grams. So 35.4 grams of nitrogen gas. Remember, it's a diatomic. And you go look on the periodic table. Each nitrogen is 14.01, and there's two of them. So 28.02 grams for every 1 mole. That will give me moles that I can then plug into Pervner. So it's a little bit extra work. So this moles, now here's the thing, you guys, and we haven't gotten much into this yet. Do not round yet. Do not sig fig this number. Write out a handful of digits because you're not finished. Blah, blah, blah. Or just keep the whole number in your calculator. So 1.26338 something, 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 something. Okay? We're not done, so you don't want to round yet. So now I have N. Now I have moles, so I can solve. I just had to do a little bit of legwork at the beginning to get it. So let's plug in. My moles are, I just did that, right? 1.2633 something, something, something. I'm just going to keep the whole number in my calculator. Moles. There's N. R is a constant, so we go back to our constants, and there are 3 different ones. How do you pick which one? You pick which one based on pressure. The pressure given in the problem was torr. Which one of these corresponds to torr? Well, that's kilopascals, right? No, that's atmospheres. Remember, millimeters of mercury and torr are the same thing. So that's going to be this guy. 62.4, and then millimeters of mercury and torr are the same exact unit. They mean the same thing. Okay, so oops. So the R constant, 62.4. Now I'm going to do the whole units so you can see how they work out over mole Kelvin. So there's R. There's T. You cannot use 35, so you add 273 to it. So 35, 273 plus 35 is 308. Sorry about this. Divided by pressure is given as 735 torr. So before you calculate, I want to show you the units. Look, mole right here and mole down here. Kelvin right here and Kelvin down here. Torr up here and torr down here. You're left with liters, which is a unit for volume. So you multiply the top and divide by the bottom. So I'll leave this up for another second before I show the answer. Ooh, I guess I don't have the answer in here. Anybody have the answer? How many sig figs am I going to use? Well, this is 3. This is 3. And when I add 273 to that, it's also 3. So your answer should be 3 sig figs. I'm getting 33.0. Anybody else get that? Liters.
I'm not going to solve this.
Yep. I have 2 confirmations of 33.0. Anybody else? Did you have a question, Nathan?
No, I'm just trying to
Okay.
So,
Plug it in your calculator. Yay, 33.0 is the winner. I have like 4 people that have confirmed. Okay, so Avogadro's law says that if you have equal volumes of gases, as long as temperature and pressure is the same, that you'll have the same number of molecules. Remember, Avogadro's number is 1 mole of anything is 6.0 times 10 to the 23rd of that thing. Now, what he came up with was this concept of standard molar volume. Okay, so let's flash back real quick. Molar volume. Molar volume, well, let's do a word we do know, molar mass. The units for molar mass are grams over moles, grams per mole. Okay, so molar volume, so notice the mass is on the top and the molar part is on the bottom, is going to be volume over mole. That's what it stands for. And when we talk about standard molar volume, it means a specific set of conditions. And those conditions are 0 degrees Celsius and 1 atmosphere, known as STP. Standard temperature and pressure is always 0 Celsius or 273 Kelvin and 1 atmosphere. Always, always, always. This is a set of conditions, okay? So what he figured out is that 1 mole of any gas at STP occupies 22.4 liters of space, okay? Now, he didn't make this up out of nowhere. I'm going to prove to you where he got this number from. So please write out the ideal gas law. Ideal gas law is PV equals nRT. Okay, and I just said he came up with the concept of molar volume, and molar volume is volume over moles. That's what we just said, liters over moles. So watch, I'm going to put my moles over here under my volume. I'm just going to move this algebraically. That gets rid of it over here, right? Now, volume over moles is molar volume. So now, algebraically, I'm going to get rid of pressure. I'm just proving to you where this number came from. He didn't just pull this number out of nowhere. So get rid of the pressure. So molar volume equals the R constant and temperature and pressure. Well, his concept is true at STP. And STP is a set of conditions that are always the same. It is 0 Celsius and 1 atmosphere. So you need to remember that. STP means 0 Celsius and 1 atmosphere. So the R constant I'm going to use is the one for atmospheres. The one for atmospheres is 0.0821 liter times atmospheres over mole times Kelvin. There's my R constant. Temperature. Now, I don't get to plug 0 into here because you can't plug Celsius in here. So what is 0 Celsius in Kelvin? Well, you take 0 and you add 273 to it, and it's 273. So this is standard temperature in Kelvin. Standard temperature in Celsius, standard temperature in Kelvin. So R times T divided by standard pressure, which is 1, right? So atmospheres cancel, Kelvin cancel, and we're left with liter, volume, over mole, mole. Calculate this out and tell me what you get for molar volume. Volume over mole is, so I'll wait till you calculate it. Yep, right? 22.4. Isn't that the number I just told you it was? So I'm just trying to show you that he didn't just make this number up out of nowhere. He used his conditions, plugged into the ideal gas law. 1 mole of any gas, 1 mole of any gas at STP will take up 22.4 liters of space. Doesn't even matter who the gas is. If it's nitrogen gas and it's at STP, 1 mole of it will take up 22.4 liters of space. If it's helium gas and you have 1 mole of it and you're at STP, it will take up 22.4 liters of space. That's this concept, Avogadro's law. Okay? So what does that do? Well, check out this problem. And we're going to do, says, what is the volume? I want to pretend like this isn't here right now. Hold on. It says, what is the volume? Oh, my bad. Sorry, one sec.
Frozen.
I know, I'm going to switch in just a second. Okay. What is the volume? So volume is V, right? Oh, whoa. So V. And I give you grams of neon gas at STP. Well, PV equals nRT. And then STP, you need to go, okay, standard temperature and pressure is a set of conditions. Standard temperature is 273 Kelvin, so I have T. Standard pressure is 1 atmosphere, so I have P. Can I find V? Okay, divide both sides by P to get volume by itself. And now, again, I did not give you moles. I gave you grams. So you have to turn grams into moles. How do I do that? 7.17 grams of neon. Neon is 20.18 grams for every 1 mole of neon. Now I'll have moles, and then I can just plug in. So 7.17 divided by 20.18. Don't round yet. So this moles comes out to be 0.3553 something, something, something. And then the R constant we're going to use is the one that belongs to atmospheres because that is the pressure unit I'm using. So again, I'll reference back. You do not need to memorize these R constants. You just need to know how to use them. This is the one that has atmospheres in it. Oops. So this is the one I'm going to use. So this is the R constant, 0.08, oops, sorry, 0.821 liter atmosphere over mole Kelvin. Temperature is 273 Kelvin. Why? Because I'm at STP. So what? That's STP's temperature. It's always that number. Divided by standard pressure, which is 1 atmosphere. So look at moles cancel, atmosphere cancel, Kelvin cancel. We're left with liters. So let's calculate it out. I'm going to wait for you guys to do this. Whoa. I got 7.96 liters. So there's something neat about being at STP. And the neat thing about STP is that 1 mole of any gas occupies 22.4 liters of space. It's like a conversion factor. So, you know, in the beginning, we had to turn grams into moles of neon to be able to plug it into PervNERT, right? So 7.17 grams of neon. And then we said neon is 20.18 grams per 1 mole. And we did this to get moles of neon. Well, if you're at STP, you don't even have to go back and plug into PervNERT because you can say we're at moles, right? 1 mole of any gas occupies 22.4 liters of space. And the reason I can do this is because of those conditions. It's less work. Now, if you can't remember how to do this, PervNERT is still going to get you the right answer. You can still always use the ideal gas law, but this is kind of like a little bit of a shortcut from being at STP. So calculate it out, and you're going to get the same exact number as we just got, the 7 point, whatever it was. Oh my gosh, my buttons on my calculator are sticking. So 7.17 divided by 20.18 times 22.4 is 7.96 liters. Isn't that what we got before?
Yes.
So the whole point is either route gets you the same answer. So you do whichever way you feel comfortable. However, be careful. You can only use this if you are at STP. You cannot use it any other time. You have to be at 1 atmosphere, 0 Celsius, or 273 Kelvin. You can't use it any other time, and you have to use PervNERT any other time that you aren't at STP. So again, I'm going to repeat, you can still use PervNERT and get the right answer if you don't feel comfortable doing it this way, but this way is a possibility.